Okay, so welcome to this new lecture. So I'll just go through the review of last lecture. In the last class, we looked at the defects in non-stoichiometric oxides. So we started talking with the metal deficient oxides, and we took two cases. So the first case in which metal vacancies were dominating effects. So in this case, again you will have either the metal vacancy formation accompanied by hole creation, or metal vacancy formation accompanied with oxidation of the metal site. So second case was oxygen interstitial as dominating effect, and in that case again you have compensating effects. Defects could be holes or oxidized metal sites, and this is a common thing in, for example, uranium oxides, which turn out to be p-type conductors. And then we looked at dissolution of foreign atoms or impurities, which are intentional or unintentional, whatever the case may be, but when you put the impurities, the impurity has its own effect. So if you have a impurity of same formula as of, or same valence as of parent lattice, in that case you do not have any defect creation, but the moment you have impurity of different valence and different formula, you have defect creation, and these are called as aliovalent impurities. And so we looked at the case of dissolution of, for instance, A2O3 in MO, and we looked at what are the possible scenarios. In both the cases we have found that A goes to M site. Now depending upon how oxygen distributes itself on the oxygen sites, so you might have case where only two oxygens occupy the oxygen sites, maintaining the stoichiometry of the crystal and side balance of the crystal. Extra oxygen goes out, creating two extra electrons. Or in the case 2, you might have three oxygens going to three oxygen sites, which means it disbalances the side balance. So to maintain the side balance, you create another metal site which is empty, so thereby giving rise to a metal vacancy. And then we looked at the cases in which the oxide, suppose the oxide has reasonable amount of vacancy concentration to begin with, or reasonable amount of hole concentration to begin with. So as an exercise, I asked you guys to discuss the dissolution of A2O in MO, and to understand the defect formation in stoichiometric form as well as in the form having prior defects. So I will leave this exercise to you, and then we worked out what was the concentration of intrinsic defect. This is a thermodynamic basis to calculate the concentration of intrinsic defects, and the basis comes from that if the defects are stable, that means at certain concentration the free energy of the crystal will be minimum, or the free energy change will be the most negative. So as a result, we worked out the expression for defect concentration, which is nothing but exponential dependence on the free energy expense and temperature, and it comes out to be delta HF in the case of Frenkel defect, it could be delta HS in case of Schottky defects. So naturally, as you see, as delta HF increases, which means as the energy expense formation per pair of defects increases, then in the formation of defects increases, then the number of defects go down, and as the temperature increases, number of defects go up. And this is something which you can look at the formula, and then you can try putting various numbers. So for instance, you can try putting delta HF. Delta HF can be something like 1 electron volt, 2 electron volt, 3 electron volt per atom, and then you can look at temperatures at various temperatures from 500 K to 2000 K, just hypothetical cases, and you can work out what is N, and then you can see how the small n, that is the number of defects, change as a function of these variables. And then we looked at the case of comparison of NaCl and MgO, and we see that NaCl has very large defect formation energy as compared to magnesium oxide has very large defect formation energy as compared to NaCl, and this is because of high melting point, which is because of high bond energy or stronger bonds as compared to NaCl. So at any given temperature, the number of defects in MgO are much smaller in number as compared to NaCl. However, if you take the same homologous temperature, in that case the defect concentration works out to be roughly equal. So, in this lecture we will just extend that a little bit, and so for now what happens is that in case of MgO it is very difficult to make it completely pure. So, in case of MgO the impurity tolerance is about 50 ppm, whereas in case of sodium chloride the impurity tolerance is about 1 ppm. Now, as a result, when you have 50 ppm impurities, and these impurities could be, for example, Al2O3. So, as a result, the defects which are created in MgO now, they are due to Al2O3, because there are two kinds of defects. Defects could be intrinsic. Intrinsic means thermally created. So, here n will be proportional to exponential of minus delta H, let us say Schottky defect, divided by kT. So, at any given temperature n will be determined by the magnitude of temperature, and then you have extrinsic. Extrinsic are due to impurities which are aliovalent. So, when you put Al2O3 in MgO, you know that Al2O3, when you put in MgO, let us say both aluminum go to magnesium site carrying one positive charge, both the oxygens, let us say all three oxygens go to oxygen site. In that case, it will give rise to another 2 electrons, or so any of these two reactions is possible. The bottom one is most likely. Now, magnesium oxide is a material as well as sodium chloride is a material. Both of them are prone to having Schottky defects. Schottky defects will be, in this case it would be Vmg plus Vo. In this case it would be Vna plus Vcl. I have not put the charges on top. There will be charged defects. Now, in MgO the thermally created defects would be Schottky defects. So, as a result you have magnesium vacancy and oxygen vacancy, and since cations are usually smaller than anions, these are more mobile as compared to oxygen vacancies. Now, similarly, now when you put Al2O3, then also you create magnesium vacancies. So, what happens is that at lower temperatures in MgO, the defect creation in MgO is governed by the proportion of Al2O3, and normally you have at least about 50 ppm of Al2O3. The concentration of vacancies is roughly similar to 50 ppm. You can see that for 1 mole of Al2O3 you create 1 vacancy. So, if you put 50 ppm Al2O3, you have 50 ppm of vacancies which are not thermally created, and if you look at the previous number in the previous slide, the concentrations are of the order of 2 to 3 ppm, which means a few ppms, let us say. So, which means the number of impurities created by number of defects created by impurities are much more larger, and this is extremely significant at lower temperatures than at high temperatures, whereas NaCl, it has only 1 ppm tolerance. So, at least even at the same homologous temperature, the impurities the defects created by impurities in MgO is about 50 times higher than in NaCl, which is contrary to just thermally created defects. So, what happens is that in case of NaCl, so extrinsic defects, these defects which are created due to impurities dominate at lower temperatures, because N thermal is smaller than N impurity, where N is the number of defects created by either impurity or thermal means, whereas at higher temperatures N thermal tends to dominate over N impurity. So, as a result, in defects you see two behaviors, one is extrinsic behavior, one is intrinsic behavior. extrinsic behavior. This replicates itself in the properties, especially like diffusivity and conductivity, as we will see later, and we will see that intrinsic behavior is more predominant at higher temperatures, whereas extrinsic behavior is more predominant at lower temperatures, where defect concentration is independent of temperature. It is dependent. So what you will see is that if you plot defect concentration, let us say log n versus 1 by T. So for example, this is MgO containing some Al2O3 x% Al2O3. So what you will see is that the concentration varies like this. So this is your minus delta HF or HS in case of Schottky defects, HS. Okay, delta HS by K, and so this goes like this. And beyond this, let us say critical temperature, what dominates is, so this is N is equal to N impurity, and this is N is equal to N thermal. So this is how the behavior is. So overall behavior is something like this. This is, so up to this temperature it's all thermal. This is 1 by T. So this is low temperature regime, and this is high temperature regime. So this behavior is called as extrinsic behavior, and this behavior is called as intrinsic behavior. Whereas for NaCl, since the impurity concentration is very small, the domination of impurities in terms of defect concentration is limited to a very small temperature. Okay. So this is the relevance of impurities in creating the defects. Now before we move on to defect equilibria into thermodynamics of defects in oxides, we will just see what are the units for defect concentration, and here N by N is nothing but fraction. So you can of course relate the defect concentration in terms of fraction, so which means ratio of number of defects to the ratio of to the number of lattice sites. However, both N and N can have units of number per cc or number per centimeter cube or number per meter cube. Okay. So you can have this, or you can have, so this is numbers, basically number per unit volume. So for instance, a typical defect concentration in ceramics is about 1 ppm. Okay, and let us say the density of solid is about atomic density of solids. Atom density of solid is equal to about 10 to the power 23 per centimeter cube. In that case, 1 ppm is almost equivalent to 10 raised to the power 17 per centimeter cube. So if you want to calculate now, if you want to convert the mole fraction to a number per unit volume, so to number per unit volume, then you can, this will be, so number per unit volume would be equal to Na, which is Avogadro number per mole, multiplied by density, which is gram per cc, divided by molecular weight, which is gram per mole. So, this will give you a number per unit volume. So, this is how you can calculate number of formula units and number of defects per unit number per unit volume. Okay, so now the next topic that we will consider is so far we have seen how to calculate the defect concentration, what are the different kind of defects and what are the defect units, and now we will see what is the thermodynamic basis of writing these defect reactions and how we can then extend this thermodynamic approach into calculating these defect concentration as a function of parameters such as pressure and temperature. So, now we will look at this is an important topic called as defect equilibria. So, first defect equilibria is nothing but our equilibrium, what happens to defects under equilibrium, and how can we represent these defects. We said that we can write these defects, formation of the defects in a solid as a defect reaction in a similar fashion as a chemical reaction. So, for that we need to establish a thermodynamic basis. How can we do that? So, first we will discuss is what is called as the topic is thermodynamics of defect reactions. So, basically a defect when a chemical reaction takes place, there is a change in free energy, right. That change in free energy is related to some thermodynamic parameters such as your reaction constant, and this reaction constant is related to the activities or the concentrations of various species that take part in the completion of that reaction. And the knowledge of equilibrium concentration and with respect to parameters is required to work out a complete defect equilibrium diagram, from which we can work out any given temperature, at any given temperature, at any given pressure, what is the defect concentration of each type in a given material. So, for instance, the most important thing is to work out in oxides is calculation of defect concentration as a function of partial pressure of oxygen, because these oxide materials are typically used at various pressures, for example, as a sensors or gas sensor in gas sensing application. So, in that case you can look at different oxygen partial pressures which defect will dominate in a particular material. So, if you want to really go into so for this we will take the approach of what is called as chemical thermodynamics or metallurgical thermodynamics, especially in solutions. So, where solutions means you have a solid containing various species 1 to n, let us say, and what happens to thermodynamic free energy in that solid and what happens at equilibrium. So, if you want to go into details of thermodynamics, if you want to understand the basics of thermodynamics, you should refer to any book on basic thermodynamics, such as the Thermodynamics by Gaskell. It's a very nice book, or Darkin and Gurry. I'll list some of these websites, I have listed some of these books in the bibliography of this course in the beginning of possibly in the first lecture, or you can just look through the internet and find some basic books on the metallurgical thermodynamics or chemical thermodynamics. So, we will start, for example, with a chemical system consisting of so assume a chemical system. This consists of N1, N2, N3 to Ni moles, and species are 1, 2, 3 I species, okay. And the partial molar free energy free energy of a particular constituent, let us say of ith constituent, is given as, so partial molar free energy is equal to chemical potential, which is, so let us say Gi is expressed as del G, which is the overall free energy, divided by del Ni at constant temperature, constant pressure, and N1, N2, Ni minus 1, except Ni, everything else is constant, and this is also equal to mu I, or chemical potential of species or entity I. Okay. Now, we can write the total, the net free energy, can be expressed as, so G is equal to N1 mu 1 in terms of chemical potential of each of these species. So, N1 mu 1 plus N2 mu 2 and so on and so forth, plus Ni mu I. This is the chemical, this is the free energy. Now, so suppose now assume the system is open. So, for an open system, considering the system is open system. Now, for the definition of closed system, I assume that you know the definition of open and closed systems from the basics of thermodynamics. So, for an open system, now I can write del G at constant temperature and constant pressure to be equal to mu 1 dN1 plus mu 2 dN2 mu I d N I. I can write dG. So, let us not make it confusing. So, dG at constant temperature and pressure is equal to mu 1 dN1 plus mu 2 dN2 up to mu I dNi, where mu is the chemical potential of each entity and N is the N1, N2, N3 and I are the concentrations. Now, from this I can write this as from 1 to I is equal to dG at Tn P, constant temperature and pressure. Now, now assume a chemical reaction. So, we are taking a system where many species are present to react and then some products form. So, assume a chemical reaction as following. So, let us say A moles of A, capital A, plus B moles of capital B react together to form C moles of capital C plus D moles of capital D. So, the free energy change that you write delta G can be written as C of mu C plus D of mu D, this is the product, minus the reactant A of mu A plus B of mu B. So, this is the net free energy change. Now, at equilibrium what happens? Okay. So, at equilibrium delta G is equal to 0. So, this we know. So, now we can write as and we know that mu I is equal to mu I naught plus RT ln AI, where AI is the activity of ith species. Okay. So, now what is activity? We know that AI is equal to gamma I multiplied by Ni or Ci, depending upon what is the convention. So, gamma I into Ni, where now for an ideal solution, where gamma I is the you can say activity coefficient. So, for an ideal solution, gamma I is equal to 1. So, AI is equal to Ni, okay, and delta G naught. So, for ideal solution, gamma I is equal to 1, and we can take then AI to be equal to Ni. Okay. So, now let us move to the next slide. So, when a system contains several phases, in that case the condition of equilibrium basically means that if you draw the free energy composition diagram, which I am not going to draw, but what it means is that the I can draw it. So, for instance, so these are the two phases. So, what it basically means is that this is free energy composition diagram, and what it means that when two phases are in equilibrium, the chemical potential of two phases or several phases is same. So, if you have two phases, then chemical potential of each constituent in both phases is same. If you have more than two phases, three phases, four phases, then also chemical potential of each constituent in all the phases is same. So, now we know what chemical potential is. So, we can write this delta G, which is the net free energy change, to be equal to delta G naught, which is the free energy change in standard state, plus RT ln K. Now, what is K? K, as we know, is A activity of A to the power A into activity of B to the we have to write the product on top, activity of C to the power C into activity of D to the power D divided by activity of A to the power A multiplied by activity of B to the power B. Okay. And assuming that it was an ideal solution, this is equal to NC to the power C into ND to the power D divided by Na to the power A into Nb to the power B. So, this is your K. So, delta G is now equal to delta G naught plus RT ln Nc to the power C and D to the power D divided by Na to the power A and B to the power B. Now, what is delta G naught? Delta G naught is the free energy change in the standard state, that is at unit activities. All right. So, and delta G naught is a constant under specified standard states, and at equilibrium we can write delta G naught as minus of RT ln K, because delta G is equal to 0, and delta G naught expression is basically C mu C naught plus D mu D naught minus, same as the free energy change for a reaction. We have a delta G naught in which is the free energy change of in standard state is equal to A mu A naught plus B mu B naught. Okay. So, so basically you have written what K is. So, now K as you know is nothing but equilibrium constant, or often referred as reaction constant, which relates the activities of products to the reactants under given conditions. So, Now I can write what is delta G naught. Delta G naught can be written in terms of delta. So further, delta G naught can be expressed in terms of delta H naught minus T delta S naught, which is the enthalpy change in the standard state minus temperature multiplied by the entropy change in the standard state, and this is given as minus RT ln K. So I can write now this as, so basically what it means is that K is equal to K naught into exponential of minus delta H naught divided by KT. And what is K naught? K naught is your delta S naught divided by R. So this is very clear, you can just divide by RT or KT here. So I will just make it R, let us not be ambiguous there. So it is R everywhere or you make it K everywhere. So it depends whether you take it per atom or per mole. So this is what is K is equal to expression of K. So K also is a temperature dependent entity. How can you show it in a more elegant manner? The temperature I can show it in a more elegant manner, the temperature dependence of K as d ln K divided by d 1 by T to be equal to minus of delta H naught by R. So this shows that the K is dependent on temperature, which is equal to minus delta H naught by R, and this is called as your this is basically a very important, this is an outcome of Gibbs-Duhem equation. And what was the Gibbs-Duhem equation? If you go to the previous slides, so this was your it's a fundamental thermodynamic relation where you relate the free energy with respect to free energy to the concentration of species and the chemical potential. So what basically this tells you is that this is an this basically tells you that just like we treat solute in a solvent in a normal material, we can treat defects in a solid as solute in the solvent. So defects in a solid are equivalent to solutes in a solvent, given that they are dilute. Dilute solutions, that is n, which is a number of defects, is smaller as compared to capital N. So this thermodynamic basis, which is established for solids or solvents containing dilute concentration of solutes, can be extended to defects, because defects are also present present in the solid in very small numbers, and the presence of these defects in small numbers can be treated as equivalent to solutes in a solvent or in a given solid. So the further so basically the formalism that we have established here, that you write a chemical reaction, so A plus B is equal to C plus D, and you write K, which is so you write concentration of C, concentration of D multiplied by A multiplied by B, and delta G is equal to minus RT ln K. So basically K is equal to exponential of minus delta G naught divided by RT. So we are going to calculate K for all the defects, considering defects formation as in the form of a defect reaction, and relate it to thermodynamic parameters such as delta G naught, which can be related to delta H naught and temperature. So, this is how we are going to treat all the defect formation in the solids. So, now what we are going to do is that we are going to establish this defect equilibrium, which we have so far understood now, in stoichiometric oxides. So, let us take first the case of defect in stoichiometric oxides. So, let us take first the case of Schottky defects. Okay. So defect reaction so consider the oxide as MO. So, what is the defect reaction in this oxide MO? I can write 0 or null to be equal to VO plus VM dash dash. Okay. Now, so VO is doubly charged vacancy and VM is doubly charged metal vacancy, or sorry, VO is doubly charged oxygen vacancy and VM is doubly charged cation vacancy. So, what is the equilibrium constant for this reaction? Now, treat this as a chemical reaction. So, equilibrium constant let us say Ks. Ks is given as concentration of VO multiplied by concentration of Vm. So, we are treating it as a normal chemical reaction, and we also knew that Ks is also equal to exponential of minus delta Gs divided by RT. Okay, just from the previous slide, we know that there is a temperature dependence of K. So, we have written now K in the form of energy change, and delta Gs was equal to delta Hs minus T delta SS, and so where delta Hs is the enthalpy change for Schottky defect formation and delta SS is the entropy change, which is mainly a vibrational entropy change, and this can be further written as, so you can write K as exponential of delta Hs minus T delta SS divided by RT is equal to let us say, so T will cancel here, we will make that at K naught exponential minus of delta Hs by RT. So, this particular thing is K naught. Okay. So, having done this, so let us say if the Schottky defect says that if Schottky defects dominate, or are the defects in majority present, in that case I can write in that case Ks was equal to VO multiplied by Vm, and we know that VO is equal to Vm, right. So, which means VO is equal to Vm is equal to Ks to the power half. So, in such a solid, VO is equal to Vm is equal to K naught to the power half into exponential minus delta Hs divided by 2 Kt. So, this VO is equal to Vm is equal to K naught to the power half exponential minus delta Hs by 2 Kt. Now, you can see many things from this. First, VO and Vm has same dependence on delta Hs and T as we calculated when we calculated the concentration of intrinsic defects in the solid. So, first we verify the correctness of that derivation. 2, there is no, so although it is an oxide MO, there is no dependence on partial pressure of oxygen. So, 1, concentration is dependent on delta HS and T, and the increase or decrease is in the same fashion as we discussed in the concentration part. 2, independent of PO2, which means wherever possible, wherever these defects are, wherever the oxide, whatever the regime in which oxide is in the stoichiometric state, and when Schottky defects dominate, the defect concentration is independent of partial pressure of oxygen. So, which means in the stoichiometric range, so let us say if this was the stoichiometric range of PO2, so this was the stoichiometric range, and if Schottky defects dominate, in that case the concentration would be like this. So, this would be within this particular range of PO2, it won't be too large, it would be around 1 atmosphere, and this would be VO is equal to Vm, and independent of partial pressure of oxygen, and this is at constant temperature. Okay. So, in the next part we will look at the same exercise for Frenkel defects. So, we will quickly go through that. So, thermodynamic equilibrium in Frenkel defects. So, again consider an oxide, consider MO. Frenkel defect reaction can be written as metal site goes to interstitial site forming having 2 positive charges, followed by metal vacancy having 2 negative charges, and the reaction constant Kf can be written as Mi into Vm, assuming mm to be equal to 1. Okay. And if mm was in very large number, which means Mi and Vm are very small as compared to concentration of mm. We know that Mi is also equal to Vm. So, as a result you can write Mi is equal to Vm is equal to Kf to the power half. And so, again you apply the same formalism, with the same formalism was that I can write Kf to be equal to Kf naught exponential minus delta Hf by Kt. Okay. And so, I just equated there. So, as a result Mi is equal to Vm is equal to Kf naught to the power Kf naught into exponential minus delta Hf by 2 Kt. So, again you see similar sort of expression where concentration is related to exponential minus delta Hf by 2 Kt, similar to expression that we derived earlier, and again there is no dependence on partial pressure of oxygen. So, concentration independent of PO2. So, depending upon which defect dominate in the stoichiometric state, in both cases the defect concentration is independent of partial pressure of oxygen. Now, let us say what happened in the non-stoichiometric states. These so these stoichiometric states are common at around 1 atmosphere, and the non-stoichiometric states, non-stoichiometric either oxygen deficient state or oxygen excess state or metal deficient, metal excess otherwise, would be possible when, so oxygen deficient would be possible when oxygen pressure, partial pressure is very low, and oxygen excess would be possible when oxygen partial pressure is very high. So we will now look at the equilibria in these non-stoichiometric states. So first we will take the case of oxygen deficient oxides. So oxygen deficient oxides means MO1 minus X. Okay. So we will take first case when oxygen vacancies dominate. Okay. So when we take that, in that case again I write the defect reaction. The writing of defect reaction is similar to what we did earlier. So formation of vacancy of oxygen plus formation of 2 electrons. So the reaction constant would be, so let us say or equilibrium constant K would be equal to VO into PO to the power half into NE square divided by OO. Now again, assuming that defects are in very small concentration as compared to OO, so we take OO to be equal to 1. So hence K is equal to VO multiplied by PO to the power half multiplied by NE square. So, so this is the expression you get. Now from this expression you can see that for each vacancy created, each oxygen vacancy created, you have 2 electrons. So eventually the concentration of electrons is 2 times the concentration of vacancies. So I can write this expression Ne to be equal to 2 of VO. Okay. So this is because of to maintain the electrical neutrality. So I can write K to be as K was equal to VO into PO to the power half multiplied by NE square. So I can write that as 2 VO square. So this would be equal to 4 VO cube into PO to the power half. Now, so what it means is that VO is equal to K by 4 into PO to the power minus half VO cube, or VO is equal to K by 4 to the power 1 by 3 into PO to the power minus 1 by 6. So assuming that K you know is again equal to exponential of minus delta G by KT. So again it is nothing but, you know, K naught into exponential of minus delta Hs by H by KT. This delta H can be determined experimentally. Okay. So which means you can determine the K experimentally. So K will be at a constant temperature, a known quantity. Okay. So which means what it tells you is that VO is proportional to PO to the power minus 1 by 6. So when you plot this concentration of, so if you take just as log scale and this is VO, so in that case you get the relation decreases like this, and this would be your minus 1 by 6. So the the concentration of oxygen vacancies decreases as you increase the partial pressure of oxygen, which is intuitively understandable, because as you are increasing the partial pressure of oxygen, basically you are pumping in more oxygen into the system. As a result, you are reducing the concentration of oxygen vacancies. So this is the dependence of partial oxygen vacancy concentration on partial pressure of oxygen in the defect in a non-stoichiometric oxide, which is oxygen deficient, and where oxygen vacancies are dominating defects. So what would be the concentration of electrons? The electron concentration would be simply this. So just a straight line parallel to this previous line. So this would be N, which is equal to 2 VO. So you have this. So the only difference now here is and also Ne is proportional to PO to the power minus 1 by 6. The only difference that you see with respect to previous case of stoichiometric oxide is, in case of stoichiometric oxide there was only temperature dependence, there was no partial pressure of there was no dependence on partial pressure of oxygen. Here not only you have a dependence on temperature, which is as a result of K being dependent on temperature, you also have a dependence on partial pressure of oxygen. So if you take this, if you plot this concentration as a function of partial pressure of oxygen at constant temperature and pressure, constant temperature, not pressure, sorry. So at constant temperature, then you see this kind of trend. The oxygen vacancy concentration reduces as you increase the partial pressure of oxygen. So this is for the case when your oxygen vacancies are dominant. What happens when your metal is in excess? So second case is, so case B is when Vm dominate. In such a case, the reaction can beMm. So we will not spend too much time in writing reactions now, because we have already understood how to write a reaction. So here your metal, now here, sorry, I am a little wrong here. Here Mi dominates. Metal excess would be Mi, not Vm. So apologies for that. SoMm plus Oo, Mi plus oxygen goes out, because to maintain the site balance, otherwise you will have a vacant site, plus you will form 2 electrons, or alternatively you could have Mi plus Oo, but that would be nothing but Frenkel defect. So okay, so this is the non-stoichiometric defect. So equilibrium constant for this reaction, K is equal to Mi PO to the power half into Ne square divided by Mm concentration into Oo. Assume that these to be equal to 1. So K is, and also to maintain the charge neutrality, you have Ne to be equal to 2 times of Mi. Okay, so I can write now K as Mi into PO to the power half into 4 Mi square, or again you can write this as Mi is equal to K divided by 4 to the power 1 by 3 into PO to the power minus 1 by 6. So either whether it is oxygen vacancies or whether it is metal interstitials in both, if the oxide is MO. So, excuse me. So, we can take in MO. So, whether it is oxygen vacancies or metal interstitial, both of them depend upon PO to the power minus 1 by 6, and as a result the electron concentration Ne will be equal to 2 Mi, which will, so Ne is also proportional to PO to the power minus 1 by 6. So, again when you plot these two, PO2 Mi or Ne, so if your, this is your, this would be your 1 by 6. So, this will be Mi and this would be Ne is equal to twice of Mi. Okay. So, this is the case when you have oxygen deficiency, which means either oxygen vacancies prevail or metal interstitials prevail. In the next class, we will look at some other cases to work out the defect equilibria in these non-stoichiometric oxides. Thank you.